Advanced Algebra Chapter 7, Lesson 2, and we want to look at rationalizing the denominator. Now, we've just spent some time looking at dividing radical expressions, and radical expressions, or a division of radical expressions, is really a fraction where you have a radical in the numerator and a radical in the denominator. And to divide, we simply simplify those radicals as much as we can within the fraction. And so far we've worked with fractions where the denominator always simplified to a 1, or they simplified to a point where you could take the square root or cube root of that denominator, thus removing the radical sign. However, if we leave a radical in the denominator, we need to rationalize that. To rationalize a denominator means to rewrite it so there are no radicals in the denominator as a final answer and no denominators in the radical of a final answer. And the reason we call it rationalizing the denominator is because we're taking a number that is irrational, like the square root of 2 or something like that. Let's say that's in the denominator, 1 over the square root of 2. We have an irrational number in the denominator. And so what we want to do is something mathematical that takes that irrational number and changes it into a rational number. So you go from irrational to rational. That's why we call it rationalizing the denominator. And we're going to do something and use a couple of properties that we know mathematically in order to do that. One property we know is that if we multiply, or if we have two radicals that are the same and we multiply them together, that simplifies to the radicand, changing or making this irrational number a rational number. In other words, the square root of 2, which is irrational, multiplied by itself, irrational, becomes a rational number 2. So we know this. The other thing that we know is that when we do something to a numerator of a fraction or denominator of a fraction, as long as we do the same thing to the other one, we're okay. So if I decide to multiply a fraction's denominator by 2, if I multiply the numerator by 2, I don't change the value of the fraction. So that mathematically is okay. So we're going to take these two things and combine them to help us rationalize a denominator, or to make sure that we don't have any radicals in the denominator, so we don't end up with something like this, and we don't have any denominators in a radical, so we don't end up with a fraction underneath a radical. These are two answers that are not simplified, and the point of what we're going to do is to simplify these so that neither one of these cases is our final answer. Okay? And in order to do that, as I said, we're going to use those two properties that we have just talked about. So if I have the square root of 2 over the square root of 3, the square root of 3 is an irrational number. If I multiply the square root of 3 times itself, that's going to simplify to a rational number. So if I multiply the square root of 3 times the square root of 3, and I do that to the numerator as well, then I have done nothing to the fraction that's changed its value. I've simply made a irrational number into a rational number. And so the simplified version then would be the square root of 6 over 3. This is a fraction that does not have a radical in the denominator, and there is no denominator in the radical. Okay, so that's the simple process. Now we are working with higher degree or higher index radicals like cube roots, fourth roots, or whatever. Now we're going to stick with that pattern. Meaning, let's say I want to rationalize the cube root of 3. Well, if I multiply this by another cube root of 3, that's only 2 3's, and the index tells me that I need 3 3's in order to have that come out as a single number. So I'm going to need another cube root of 3 in order that if I multiply these together, now I have the cube root of 3 3's, which does simplify to a single number 3. So if I had a fourth index, I would need 4 fourth roots of 3. If I had a fifth root, I would need 5. So we're going to have to multiply by as many radicals that we need in order that the index requirement, so to speak, is met, and then we can actually rationalize the denominator. Before I do these examples, I want to give you one tip that will save yourself a headache. And that is to, much like I said before, that we want to simplify before we multiply. You want to simplify before you rationalize. Okay? Simplify before you rationalize. It will save yourself a headache. And in many cases, it will even create a problem where you won't even need to rationalize anymore, because by simplifying, the radical in the denominator goes away. And you notice that in those few examples that we did when we were dividing. Every time we divided, we ended up with a denominator that did not have a radical in it anymore. So we didn't even have to rationalize, because the simplification process took care of that. So before you start going to rationalizing, do the division, the simplifying, simplify all you can. Simplify by dividing, okay, reducing variables and things that are the same, and then once you've done that, even before you rationalize here, go ahead and simplify the numerator radical if you can, and denominator radical. And after you've done everything that you can, if at the end you're left with a radical in the denominator, then rationalize at the end. But don't jump right in and rationalize first. That will cause you a lot of headaches, a lot of problems. It creates bigger numbers and more variables, and can really cause just a plain lot of headache. But if we simplify everything first and rationalize as the last thing that we do, it's going to make life a lot easier for us. So let me do a few examples, and hopefully you'll see what I'm talking about. So let's take a simple example to start with. Let's say we have the cube root of 4 over the cube root of 6x. Now, because these are both cube roots, I want to simplify first. So 4 and 6 are both divisible by 2. So if I'm going to divide that, I can reduce that by 2, reduce that, I have the cube root of 3x, all right? So I've done all the simplifying I can. I still have a denominator here with a radical. Now the index is 3. That means that I need 3 3's and 3 x's in order for them to take the cube root. So that means I need 2 more 3's and I need 2 more x's in order for these values to come out. So if I do that to the numerator or denominator, I have to do it to the numerator. So I need 2 more 3's and 2 more x's. Now that I've done that, so I can multiply these together. So in my numerator, I have the cube root of 2 times 3 squared. So 3 squared is 9, times 2 is 18, and then I have x squared. And then these, I now have 3 3's in my denominator, so the cube root of 3 3's is a 3, and the cube root of x cubed is an x. So this would be the simplified version, and then the denominator rationalized for this example. Okay, so I have the cube root of 18x squared and 3x. Now again, the simplification process first, and then rationalize the denominator last. So let's look at number 32 here. Now again, before I jump right in and start rationalizing this denominator, let's simplify everything that we can first, all right? It will make my life easier if I do that first, okay? Now, I can reduce non-radicals with non-radicals. So 15 and 3, I can divide both of those by 3, leaving me 5 in the numerator and a 1 in the denominator. The square roots I can simplify. 12 goes into 65 times, so I can simplify that with 1, so then I have the square root of 5. And then I can simplify 1x with one of these, take 1 away from these, that leaves me x to the 4. Now notice, by simplifying, this denominator is 1, I've eliminated the need to even rationalize the denominator. Okay? By simplifying first, I don't even have to use the whole multiplying by 12x and then reducing those bigger numbers. I simplify it first. It creates something that's much smaller, much easier, sometimes even eliminating the need to even rationalize the denominator. So simplify before you rationalize. Now remember, now that I've done the simplification, I do have to look and see if there's anything else I can do. I can't take the square root of 5 because that's irrational, so that stays. However, the square root of x to the 4th is x squared. So this is the simplified version, the rationalized denominator, all of it done without actually having to rationalize the denominator. Okay, so always take care to simplify before you rationalize, and it can save you a few headaches in the long run.